Hey you all, this is Celso Batalha, and this week or today we are focusing on stellar properties. How in the world we know about stars if so far we don't have the technology to even visit the sun, a star that is right there in our backyard? How do we know so much about stars? So this chapter is very important because it introduces and explains the basic tools astronomers use in order to infer properties of stellar objects. Or if you think about galaxies, for instance, galaxies are a combined result of hundreds of billions of stars. So if you know what a star is and what properties a particular stars have, you can add up that to 100, 200 billions of times and see what's the final result of it. Um, so this particular chapter explains not only how telescopes are important, because telescopes, as we saw before, are instruments used in order to capture light. In this chapter, what we're gonna do is say, hey, um, we know about light. We know how light interact with matter. Excuse me. So how can we use this knowledge in order to infer properties of objects we haven't visited yet? Remember, in one of the past lectures I mentioned that astronomy is an important science, perhaps the first formal science that our species developed, and it's kind of a different from the other ones. The other science, you go out and you collect data, bring to the laboratory, and then you sniff, you open, you dissect, you touch it, you smell, you have physical contact with your subject, with your data. Um, in astronomy, we don't. I mean, do you know anybody who went out there and brought a piece of a quasar to the laboratory? I don't think so. So how do we know about quasars? How do we know about Big Bang? How do we know the universe is expanding? We haven't been there. We haven't traveled through space and time. But we know because we know about light. So that is the main subject of this chapter. And what's going to be the assignment today? Well, you just wait. I don't know yet. I will go by the year. What is this? Oh, it's a proper motion. Okay, let's just open the PowerPoint. Let's see what I. Just a second. I have to get myself organized. There you go. Here's the PowerPoint, chapter 10. And okay, first thing, parallax. What parallax is all about? What's the importance of parallax? Here it is. Parallax. What that is? Well, you know, think about an experiment we can do now. Take you don't need to do what this guy. This guy has a pencil, right? You don't need a pencil. Just take two fingers, your right and left pointing fingers, and put them at arm's length with a small separation, as you can see. And then, in fact, I'm doing the same experiment right now. Okay, so do that. I mean, make sure no one is looking at you. They think you are kind of a crazy. But you know, put your fingers pointing up, the pointers. I have my left hand kind of ahead of my right hand, and I have the two fingers kind of slightly separated. So what I'm doing now is closing my left eye and then looking and see where my fingers stand in respect to the background, which is a wall that has a metals. I'm standing in my kid's room, and there are a bunch of hanging medals there, soccer, you know. So what I'm doing now is keeping the fingers in the same position. I'm opening my left eye and closing my right one. So what do I see? Oh, geez, did you do that? What did happen? Okay, so same thing happened to me. So when I open um, the right eye and close the left one, my fingers moved in respect to the background I was looking at. So kind of it is shown here in this picture, right? So you have the two pointed fingers and you have background things, my wall with the metals hanging down. I don't know what you got there, but um, pretend now these are not your eyes, but is Earth orbiting the Sun with a time base of 6 months, right? So Earth takes about 1 year to complete an entire revolution around the Sun. So let's say this is your right eye, this is your beautiful nose, and this is your left eye, okay? And here is my right finger and my left pointed finger. And here's the wall where the metals, in my case, are hanging now. So when I observe these two pencils by closing my left eye, that's the first thing I did, I think. What do I see? Well, I see these two stars. I see these two stars projected somewhere in here. Is that correct? But see, if I wait for 6 months, Earth's gonna be in this position, and now what do? I close my right eye, and then by looking at these two stars with my left eye, I see them projected in this part of the sky. And then 6 months later, I do the same exercise, and boop, stars are back to where they were before. So this relative motion of star A and star B, or finger A and finger B, in a time scale of 6 months, back and forth, it's called parallax. Now, I don't know if you are good in geometry, or if you studied trigonometry before, or if you ever saw geometry in the past. If you did, great. If you did not, just trust me, because Greek philosophers and mathematicians, hundreds of years ago, in fact, they knew about geometry, right? Thousand, at least 1,500 years, 2,000 years ago, they knew about geometry. And look at this. Do you know the distance between Earth and the Sun? One astronomical unit, right? We learned that in chapter 1. So if you know this distance, if you happen to go in the sky and measure this relative motion right here in arc seconds and an angle, I mentioned before that if you make a fist at arm's length, that fist projects in the sky 10 degrees. 10 degrees, right? So if from horizon to horizon, east west, you have 180 degrees. So 18 of these fists passing through your zenith point, right, from east to west, passing through your zenith point, you should probably do 18 of these fists, because you have 180 degrees up there. Does that make sense? So 10 times 18, 180 degrees, with half circle. Now, so sky, we don't know distances or relative distances of objects, but we can think about angular separation. Excuse me, angular separation. And so we can divide the sky in degrees, arc minutes, and arc seconds. So this angle here can be measured, if you have good technology, in arc seconds. So we can measure this angle. And where is this angle? It's right here. Is this whole thing. This whole thing right here that I'm showing with the cursor, right? So half of this angle, half of this entire angle, so half of it, which is, take this angular separation divided by 2, appears right here, right? And this angle, according to trigonometry or geometry, is equal, in fact, the tangent of it. But for a small angle, this angle is exactly equal to this distance, which we know, divided by this distance, which is the distance between star A and the Sun. In other words, if you measure this angle, which we call parallax, this angle is parallax. If we measure this angle, since we know this distance, we can infer the distance of star A to the Sun. Cool, huh? So you don't need to go to the star or go out in space carrying a ruler to measure the distance between the Sun and star A. Don't need to do that. So we don't need a spaceship. In fact, if you set a ruler on the sun, it would burn out. It wouldn't work anyways. But the point is, here, just by observing relative position of stars in the sky on a time base of 6 months, you can determine distance from the sun to that star, because technically, or by assumption, we know the distance of Earth to the sun, right? So Galileo Galilei in the 1600s, he tried to do that. The problem is he had a 1-inch telescope, not efficient to be able to devise these tiny motions, or apparent motions, seen in the sky. It was not efficient. And in fact, only in the 1840s, somewhere around that time, is that scientists start to measure position of stars with very good precision, using not telescopes, but using instruments, astrolabes and meridian circles and things like that. And in only late 1800, when photographic plate started to be used by astronomers to detect position, and in fact was largely used through the beginning of 20th century. Now basically we use CCDs, charge coupled device, which we studied in chapter 4. um, that's what astronomers use in order to imprint information, right, in computers, like the same technology you have in your cell phone or a camcorder. But so 1800, parallax started to be measured, meaning in the beginning of 20th century, in the 1900s, we have good precisions in or we have good measurements of distances to nearby stars using parallax. Okay, so let's move on. What is parallax? Let me see. The distance from Earth to the Sun. No, the shift of in position of an object caused by the observer motion. This is a good one. I like that one. The change in the distance to an object caused by Earth's spin. How can somebody write that? The change in the distance to an object caused by the sun's motion around the galaxy. Whew, God. All of the above? No way. Okay, now, brightness. Those terms are important. They are very important, because look at this. When you go out in the night sky, and you just look and pretend now it's night, right? And then you go to your backyard. Nah, don't do that. Since we are using imagination, we can be a little bit more wild. So let's go to Yosemite Park, in an area that is completely devoid of artificial light. Not only that, the moon is not in the sky. Okay, so we are in Yosemite Park, and not that cold as it is today, but it's kind of a warm, and you just lay down in the grass and then you look up to these heavens and you see all these stars. So what do you perceive? You perceive stars with different brightness, right? Let me see if I can bring that alive. Just a second. Okay, I have the Starry Night software. So pretend you are in Yosemite Park, and it's funny, there is which day is today? I'm taking December 21st because I have, the sun lower in horizon. It's kind of easier to see cool things there. And so in my left hand side I have Milky Way galaxy, this fuzzy thing up here. Orion is there, Sirius is right here. See, there is a comet there. Lovejoy comet, magnitude 6. That's cool. What else? Taurus is right there. So we see all these beautiful things, right? Let me just be a little bit more realistic, and because I mentioned Yosemite Park, right? So let's enhance the stars, for God's sake. Oh no, there you go. Okay, that's Yosemite Park. So bright, and then you can even see stars of different coloration. Yeah, stellar properties. We are going to study why stars have different coloration. But you see all of that. Look at this. Imagine, pretend you are seeing this. You know, this nice display right there. Now tell me one thing. Can you infer distances just by looking at them? No. Can you find out how big these objects are? No. Do you know anything else about them? No. What's the only thing you can tell for sure about these objects? The only thing you can tell for sure is called brightness. How bright they are. For instance, Aldebaran right here, this star, is much brighter than this star, which is not as bright as this one, which is probably, well, I think these two stars, Betelgeuse and Rigel, Betelgeuse and Rigel, they have probably same brightness, right, in the sky. They appear as bright as they are, but we don't know their properties. So the only thing we can tell is brightness. So how much energy? Think about energy now, and pretend you have a telescope that has a camera that can collect photons, particles of light, of these sky objects, so that you you can you can measure how many photons arrive at your CCD from each one of these objects. So by counting these photons, these particles of light, in a certain amount of time, you can figure how much energy you receive from those skies objects, and that is called or translated into brightness. So let's go back to here. So brightness is is what you see, and astronomers converted this measurement in brightness into a scale called magnitude scale. And this magnitude scale, for historical reasons, and because the amount of energy received is not that much. See, for instance, if you turn on a light bulb, 100 watts light bulb, in this experiment, which means go back to Yosemite Park, and let's say a friend of yours, I mean, you are in nirvana, right? You are in nirvana, you are pretty much in the heavens, contemplating all this beauty, all these stars. And then a friend of yours come and light up a 100 watts light bulb. What's going to happen? Well, first of all, you're going to get angry, and if you are a short-tempered person, you're gonna get so crazy. You're gonna say something nasty to that friend of yours. But the main point is, physically you won't be able to see the stars anymore. Now, are stars more energetic than 100 watts light bulb? Of course not, right? It can be, but why the 100 watts light bulb overshine and take over the entire sky? Well, because the light bulb is closer. The amount of energy you receive from it is much larger than it is that from stars out there. So, um, so distance is an issue here when we actually talk about energy, not when we talk about energy received in your detector on your CCD. Okay, so brightness. So astronomers, what they did, since the amount of energy we receive from stars, from galaxies, and from quasars, it's very tiny energy, very small numbers. They convert that to a scale called logarithmic scale. And the funny thing about this scale is that I always get the wrong one. Is that it goes in a way that the bigger number implies fainter object, and the smaller number, even the negative number, implies in the brighter object, right? So what is the brightest star in the sky, or the brightest object in the sky? Is the sun. The sun has an apparent magnitude that is a negative number. In fact, is the smallest negative number there is, because sun is the brightest one. Galaxies, for instance, like those Hubble telescope observe, they I mean, they are a collection of hundreds of billions of stars, but they are very faint because they are too far away, meaning the magnitude of a galaxy is a very large number, 30, number 30. Okay, so this is a so-called apparent magnitude scale. Absolute magnitude scale is, well, pretend you take all objects and you place them at 10 parsecs, which is 10 times 3.26 light years, 32, about 33 light years away. You place all the objects in there. and what's going to be their apparent magnitude. So that's the so-called absolute magnitude scale. So it implies you know distances in there. Luminosity is very important. Luminosity is the actual energy the object itself sends out to space. Okay, so brightness or apparent brightness is what you detect of that object. Like I have 100 watts light bulb and I have a very tiny amount of energy that Aldebaran is send it and I'm collecting here because Aldebaran is too far away. And another thing is luminosity is the intrinsic energy the object itself emit. So a 100 watts light bulb emits 100 ergs, a unit of energy per second. Now stars emit 10 to 30 times more than that, right? Or somewhere around that number. So they overpower uh, a light bulb. So when you think about energy the stars exactly emit, of course the luminosity is much larger. So let's keep going. Oh, I want to. Okay, it's a joke. This is your assignment. You're going to answer this question. The answers to this question. Can you answer? No, there are no questions. There are only answers. What are the questions? What's going on here? Oh Lord. Okay, first properties. Um, Let me show you this Starry Night again. So look at the stars. There is something interesting, and that is some stars appear to be yellowish, some stars appear to be white, some of them are bluer. Now, if I double click here, of course we can't do that in Yosemite Park. We can't double click stars. But it gives me properties like the temperature of the star is about 3500 Kelvin. It's a yellowy star. So let me take another one like Rigel. No, Betelgeuse. Take Betelgeuse. What's going to be the surface temperature of Betelgeuse? Oh, about the same thing, 3500 Kelvin. What is the surface temperature of a Rigel, which is a whiter star? 9000 Kelvin. And how about Sirius? Oh, I don't have the temperature. Oh, I do? No, I don't. How funny. I should have information. I don't have. But Sirius is about 10,000 degrees Kelvin as well. Somehow it's not given. Funny. So this simple exercise show that the redder this, for instance, see this red star here? Let me double click, and I bet you it's gonna give you a very low temperature. 3200 Kelvin. So the law is that the redder the star is, the cooler it is, the bluer it is, the hotter it is. Okay. This stellar property is derived from photometry. So you, in fact, what you do, you take um, telescopes, point at the stars, and then you use filters. Filters. There is a filter, a color filter in the blue, and in the yellow. Let's just make it simple. A yellow and a red, and then you collect and you count the number of photons, the amount of energy you receive through using these filters as windows that you collect energy exactly in those particular color ranges, right? In the red, in the green, or yellow. I'm sorry, blue, yellow, and red. And for instance, if a star um, sends out more energy in the red than it is in the blue, that star is cooler than another star that sends more energy in the blue than it is in the red, right? So you can use what's called color indexes, comparing the magnitude or subtracting the magnitude on these particular color bands. And by doing so, you can pin down the surface temperature of the star. So again, you don't go to the star with the thermometer, stick it in the stellar core, and say, okay, what is the temperature? Like you do with a patient if you're a doctor. I don't think you are on track to be a medical doctor because you are taking this class, right? So this is a class for non-science major. Are you going to be a doctor, a medical doctor? Well, but if you're going to be a father or mother, or if not, if you're a friend, you might have, used the thermometer to stick in somebody's mouth or arm. Or now we don't use even that. We use infrared sensors. You can get people's temperature without doing that. But anyway, so just imagine for a while that you get a thermometer, stick in the star. It couldn't even measure temperature because thermometer would vaporize. Stars are vapor, very hot. But what's the main point here? Is you can use a telescope, you can use filters, and then you can measure the amount of energy in different filters, and by doing so you can pin down surface temperature, another stellar property. You don't need to go there. Now, atoms. Matter is made of little tiny atoms, and these atoms, they can be excited when electrons are moving from ground, from lower level stage to higher level stage. It's called excite. So excitement, not excitement, excited. So when atoms get energetic, they do so by forcing electrons to go from specific orbitals to orbitals that are more energetic. And when this electron uh, cascade down to ground levels or to lower levels, they emit energy. And this is your assignment for today. Um, Review this last part, and I will talk more about, because I don't want this tape to be too long. I will review the subject in ccconf.org if you have any question for it. But what I want you to do is, for the assignment today, you go to this Astro Tour, atomic level, energy levels, and light emission absorption, and watch it. And in the section 203, it explains the difference between emission spectra, absorption spectra, and I want you to experiment, do some experiment in there. You have to watch it. I mean, this Astro Tour does not go all the way to the end in few seconds, right? So you have to hear every single part of it and then click forward once a section is over. So in the section 2 of 3, it explains and you demonstrate exactly what happened. And the main point of this assignment is to explain how astronomers can infer um, the properties of the material of stars using a spectroscopy, basically. So spectroscopy is a science by which white light or the light of objects are differentiated, created. We use instruments like prism or grating to create a rainbow of the white light. So we open the light in all its different frequencies, and then we look carefully there, and then we find absorption or emission lines, and this a simulation explains or shows well what that is. And again, in the CC Conf, I will explain that again, and how light interacting with matter takes out information of the material states like temperature, like movement, and all of that, and imprint that into the light itself. So when astronomers use telescopes and collect the light, in fact, they are collecting information, and they are trained to learn to read out that information. And that's how we know so much about quasars, galaxies, and the universe in large scale without even going there. Cool, huh? Okay, that's all. That's all she wrote.